engineeringmindset.com. In this video, we're going to be looking inside one of these, the thermal expansion valve by Danfoss. Coming up, where do we find them, what are they used for, and then the video description below. Expansion valves sit between the condenser and the evaporator in a refrigeration cycle. In this model, which is a T2 thermal expansion valve, we have the main body, which is made from brass. On the body, we have the refrigerant inlet at the bottom of the valve, then the refrigerant outlet at the side. And on the other side, we have a cap which can be removed. Under that cap is a screw which is used to manually adjust the superheat. We'll see how that works later on in this video. On the top, we have this large head called the power head. There's also a coil of very thin tubing known as the capillary tube, and there is a large bulb at the end of it known as the sensing bulb. These are all made from stainless steel. The coil is stretched out so that the bulb sits at the exit of the evaporator to sense the superheat. We have previously covered in great detail how thermal expansion valves and electronic expansion valves work, as well as the different types of expansion valves used on chillers. Do check those out, links are in the video description below. What are expansion valves used for? Expansion valve liquids cannot be compressed, so if they enter the compressor, this can cause severe damage and even destroy it. The bulb is filled with a refrigerant which is kept completely separate to the refrigerant in the rest of the system. These two refrigerants never meet or mix, they are always separated. The superheat boils the refrigerant inside the bulb, and as it boils it creates pressure. The pressure travels along the hollow capillary tube and into the power head. The power head controls the flow of refrigerant, and we'll see inside that later in this video. We place a removable cartridge inside the inlet of the expansion valve. This has an orifice which works with the valve to control the flow of refrigerant. There are different sized ones depending on the cooling capacity and the refrigerant being used. Okay, enough about that, let's cut it open and look inside. I'll just put the valve into a bench vise to keep it steady while I cut it open. Because of the delicate parts inside, I'm going to use a hacksaw to cut this one open. It does take a little longer, but the angle grinder could rip apart the internals and I want to be able to show you these parts. Okay, that's the first cut done. I'll just rotate that in the vise to cut the other side open. Again, I'm just going to use the hacksaw here to cut through it. That's pretty much cut now. I'll just use a chisel to snap the last little bit inside. And there we go. So let's have a closer look inside. So we have the main body which holds everything together. We have the refrigerant inlet coming in from the bottom of the main body in this vertical pipe, and then the refrigerant outlet on this horizontal pipe. So the refrigerant comes from the condenser and enters the valve body via the inlet. It enters as a high pressure, medium temperature saturated liquid. It then passes through the valve body, and when it leaves, it exits the valve through the outlet and will now be a low pressure, low temperature liquid vapor mixture. So what's causing the change in pressure, temperature, phase and also controlling the flow of refrigerant? Well, we can see this small pin here. This is connected to the diaphragm up in the power head. The diaphragm is a thin sheet of flexible metal. As the diaphragm moves up and down, it causes the pin to move up and down also. Underneath the diaphragm, we have a spring which is pushing up against the diaphragm. We can use this to adjust the superheat, and we'll look at that a bit later in this video. Above the diaphragm, we have this empty chamber which is connected to the capillary tube and then the sensing bulb. The chamber, the capillary tube and the bulb are all hollow. I'll just cut through the sensing bulb using an angle grinder to show you the inside. As you can see, it's just an empty cylinder which is usually filled with some refrigerant. The refrigerant in the bulb and capillary are completely separated from the main refrigerant which flows in the system. This isolated refrigerant only moves between the bulb, the capillary tube and the top of the diaphragm. The sensing bulb sits at the outlet of the evaporator. As the cooling load on the evaporator increases, the superheat increases at the evaporator outlet. Because the sensing bulb is in direct contact with the pipe at the evaporator outlet, the thermal energy transfers and causes the refrigerant inside the sensing bulb to expand and boil. Because the sensing bulb, capillary tube and the chamber are all hollow and are a sealed system, as the refrigerant expands and boils, it causes the pressure inside to increase. This pressure travels along the capillary tube and makes its way to the chamber above the diaphragm. As the pressure increases, it pushes down on the diaphragm and this pushes down on the pin. The pin controls how much refrigerant can flow, but to do that we need one more part. Inside the inlet of the valve we place an orifice assembly. Inside is a small strainer which protects the valve from blockages. Then there's a small orifice or hole which is blocked by a spring-loaded stopper. Our pin in the main valve pushes down on this stopper to open the valve. The further the stopper is pushed down, the more refrigerant can flow. As the cooling load increases on the evaporator, the superheat increases at the outlet. The sensing bulb at the outlet detects this and the refrigerant inside boils, causing an increase in pressure along the capillary tube. This pressure pushes the diaphragm down and that pushes the pin down, which opens the valve and lets more refrigerant flow. As more refrigerant flows, the superheat decreases and so the pressure in the sensing bulb and capillary tube decreases, which means there's less pressure pushing the diaphragm down. The spring then pushes the diaphragm back up, which causes the pin to move up, and as the pin rises, the spring-loaded stopper begins to close the orifice, which reduces the amount of refrigerant that can flow. This repeats constantly and stabilizes the valve to ensure the correct amount of refrigerant can flow. We mentioned earlier about adjusting the superheat control. Well, this plug on the side is threaded internally, and if we rotate this, we can move the slider up or down depending on which way you rotate it. As the slider moves up and down, it changes how much force the spring is applying to the underside of the diaphragm, which changes the sensitivity of the device and allows you to therefore tune the expansion valve and adjust the superheat. I just want to remind you that you can download the TXV Superheat Tuner app for free by clicking on the link in the video description below. Okay, that's it, but if you want to continue your learning, then click on one of these videos on screen now and I'll catch you there for the next lesson. Don't forget to also follow us on Facebook, Twitter, Instagram, as well as theengineeringmindset.com.